The industry recommended limit for single-phase power utilization for a single load is generally 12.5 kilovolt-amps, which is equivalent to 10 kilowatts. There are several reasons for this limit. Firstly, voltage drop is a concern. Single-phase loads draw uneven current from the phases, which can cause voltage drops in the circuit. Exceeding the limit can result in significant voltage fluctuations affecting the performance of other equipment connected to the same circuit. Secondly, power imbalance is another factor. Single-phase loads can cause power imbalances between the phases, leading to potential equipment damage and reduced efficiency. Thirdly, circuit overloading is a risk. Exceeding the recommended limit can overload the single-phase circuit, leading to overheating, circuit breakers tripping, or even fires. Fourthly, single-phase loads generate harmonics, which can interfere with other equipment and degrade power quality. Higher power levels can amplify these harmonics. You should consider transitioning to three-phase power under the following conditions. 1. When the single load power requirement exceeds 12.5 kilovolt-amps or 10 kilowatts. 2. When significant voltage drops or power imbalances occur on the single-phase circuit. 3. When future load expansion is anticipated. 4. When the load is sensitive to power quality issues, such as motors and drives. 5. When the facility has three-phase power available and it is cost-effective to upgrade. Also, local regulations and utility guidelines may have specific limits or recommendations, and the actual limit may vary depending on the specific load type, wiring, and circuit breaker protection. It is always advisable to consult with a qualified electrician or electrical engineer to determine the appropriate power source and configuration for a specific application. The 2008 National Electrical Code, or NEC, provides guidelines for electrical installations, including considerations for single-phase and three-phase power systems. While the NEC doesn't explicitly state a hard limit of 12.5 kilovolt-amps or 10 kilowatts for single-phase loads, it provides requirements and recommendations that indirectly lead to this general guideline. To elaborate on the factors that influence the transition from single-phase to three-phase power, let's consider some of the relevant NEC articles and related electrical engineering principles. First, voltage drop is a critical consideration. NEC section 210.19 8.1 states that the conductors for branch circuits shall be sized to prevent a voltage drop exceeding 3% at the furthest outlet for power, heating, and lighting loads, or combinations of these. Furthermore, the maximum voltage drop for feeders and branch circuits combined should not exceed 5%. When a single-phase load is excessively large, the current draw can cause significant voltage drop, particularly over long distances. This voltage drop affects the performance and lifespan of electrical equipment. Three-phase systems, particularly those with higher voltages, are more efficient at delivering large amounts of power with less voltage drop due to the reduced current for a given power level. Next, power quality and imbalance are important. Single-phase loads connected to a three-phase system create an imbalance, which can lead to several problems. Uneven loading of phases causes increased neutral currents, potential overheating of transformers, and voltage imbalances. Voltage imbalance can negatively affect three-phase equipment, especially motors, leading to reduced efficiency, increased operating temperatures, and shortened lifespan. NEC section 450.3 addresses transformer protection, which becomes critical when transformers are subjected to imbalanced loads. Also, harmonics are another concern. Nonlinear single-phase loads, such as electronic devices, variable frequency drives, and some lighting systems, generate harmonic currents. These harmonics can distort the voltage waveform, causing problems for other equipment on the same electrical system. Harmonics can lead to overheating of transformers and conductors, misoperation of sensitive electronic equipment, and increased energy losses. Mitigation techniques, such as harmonic filters or reactors, may be required, adding to the cost and complexity of the system. Three-phase systems generally handle harmonics more effectively due to phase cancellation effects. In addition, circuit loading and capacity should be considered. The NEC provides guidelines for the maximum loading of branch circuits and feeders. For example, Section 210.22 specifies that the load on a branch circuit shall not exceed 80% of the overcurrent protection device rating when the load is continuous. A large single-phase load can easily approach or exceed these limits, necessitating a transition to a three-phase system to distribute the load more efficiently and safely. Furthermore, future expansion should be planned for. When designing an electrical system, it's crucial to consider future load growth. If there's a possibility of adding more significant loads in the future, it may be more cost-effective to install a three-phase system upfront rather than upgrading later. This approach avoids the disruption and expense of replacing single-phase equipment and infrastructure. Also, equipment sensitivity matters. Certain types of equipment, such as motors, variable frequency drives, and sensitive electronic devices, are more susceptible to power quality issues. These devices often perform better and last longer when powered by a balanced three-phase system with stable voltage and minimal harmonic distortion. In these cases, transitioning to three-phase power is not just about capacity but also about ensuring reliable and efficient operation of critical equipment. Moreover, cost-effectiveness should be analyzed. The decision to transition to three-phase power should be based on a thorough cost-benefit analysis. This analysis should consider the initial cost of upgrading the electrical infrastructure, the long-term operating costs, the potential for energy savings, and the impact on equipment lifespan and reliability. In some cases, the higher initial cost of a three-phase system may be justified by the long-term benefits. To further clarify, let's look at some practical examples. Consider a small manufacturing facility that initially uses single-phase power for lighting, small tools, and office equipment. As the business grows, the facility adds a large single-phase welding machine with a high current draw. This load causes voltage drops and overheating of the existing single-phase circuits. In this scenario, transitioning to a three-phase system would provide a more stable and reliable power supply, reducing voltage drops and preventing circuit overloading. Another example is a commercial building that uses single-phase power for air conditioning. As the building's cooling needs increase, the single-phase air conditioning unit becomes inadequate. Upgrading to a three-phase air conditioning system would provide greater capacity and efficiency, reducing energy costs and improving comfort. When evaluating the transition to three-phase power, it's also essential to consider the available voltage levels. Single-phase power is typically available at 120 volts or 240 volts, while three-phase power is commonly available at 208 volts, 480 volts, or higher. The choice of voltage level depends on the size and type of load, the distance from the power source, and the local utility standards. Higher voltage levels are generally more efficient for transmitting large amounts of power over long distances. In addition to the technical considerations, regulatory requirements may also influence the decision to transition to three-phase power. Local electrical codes and utility regulations may specify limits on the size of single-phase loads or require three-phase power for certain types of equipment or applications. It's essential to consult with local authorities and utility providers to ensure compliance with all applicable regulations. Finally, it's crucial to involve qualified professionals in the design and installation of any electrical system, including the transition from single-phase to three-phase power. A licensed electrician or electrical engineer can assess the existing electrical infrastructure, evaluate the load requirements, and recommend the most appropriate power source and configuration for a specific application. They can also ensure that the installation complies with all applicable codes and standards, ensuring the safety and reliability of the electrical system. In summary, while there's no hard and fast rule, the 12.5 kilovolt-amps or 10 kilowatt guideline serves as a practical threshold for considering a transition from single-phase to three-phase power. This decision should be based on a comprehensive assessment of voltage drop, power quality, circuit loading, future expansion plans, equipment sensitivity, cost effectiveness, and regulatory requirements. Consulting with qualified professionals is essential to ensure a safe and reliable electrical system.